Hello, and welcome back to Applied Calculus. So in the textbook, we're skipping ahead with this video. It's section 6.2. It's the only part of chapter 6 we're doing just because it's so important to business applications. And I'm talking here about the area between curves. I just told you in the last video, if you're watching all of these, that area is really important in economics. And that is true. I told you no lies, but it's very frequently not area under curves. Rather, the regions we care about are very frequently regions between curves. That is, we'll have one function f of x, and we'll have another function g of x, and the region trapped between f and g has some real world significance in the economic problem you are considering. Not just economics, of course. The application I'm going to show you is from economic theory, though. That will be a video of its own. So let's jump right into it. Say that one function is bigger than another function. F of x is bigger than g of x on some interval from A to B, then the area between f of x and g of x is the definite integral from A to B of f of x minus g of x. So, I mean, just as a very quick example of this, let's let f of x be x squared, g of x be 1 divided by x on the interval from 2 to 4. What's the area between these curves? Now, don't get caught up in the fact that I used f and g up here. The actual formula is that one of these curves is above the other curve, and we're subtracting the lower curve from the upper curve. So we have to figure out which curve is the upper curve and which is the lower. Maybe it's intuitively obvious. Maybe it's not. We could graph it. If we graph it, we see that the quadratic x squared is bigger than the inverse function 1 over x on the interval from 2 to 4. So the upper minus the lower, we're going from 2 to 4. The upper is x squared, the lower is 1 minus x. And then you take this integral. 1/3 x cubed minus the natural log of the absolute value of x from 2 to 4. And we get an infinite decimal about 17.97. It might have occurred to you that the problem we just did is a little different from the picture I first showed you. In the picture I first showed you, these functions enclose a region very naturally. I didn't tell you what A was, I didn't tell you what B was, but we can talk about the area between these curves and have it make perfect intuitive sense. And this is something you see a lot in application where two curves genuinely enclose a region. And you see that this region begins where F and G intersects, and it ends where F and G intersect. So if we want to know the area between the curves, and we have a picture like this, to find the limits, we have to set f of x equals g of x. Having said that, if f of x and g of x are at all complicated, this is a pain. And I'm going to steer you towards using technology rather than trying to do it by hand. And let's give a second example to verify what I'm talking about. Let's find the area of the region enclosed by the curves p of x equals x squared minus the square root of x, and q of x equals the square root of x. And you see, I haven't given you in the problem any limits of integration, but these curves do just enclose a region. Let me see if I can shade it for you. P of x is the lower function, and q of x is the upper function. So, did not mean to do that. Trying to share the document camera. The integral is the upper function minus the lower function. So, the square root of x minus x squared minus the square root of x dx. But what about the limits of integration? Well, this region begins and ends where these curves intersect each other. So algebraically, to find the limits of integration, we would set x squared minus the square root of x equals the square root of x. But actually solving this is a pain. So when I said that I direct you towards technology, you know, this Desmos, if you know Desmos knows that we care about curves intersecting each other. So if we just click on this graph near this first point of intersection, it will just pop up for us. And we probably could just have seen this graphically, that this region starts at x equals 0. And you see now there's a gray dot at this second point of intersection. It ends at about 1.5874. So the integral from 0 to 1.5874 of the square root of x minus x squared minus the square root of x dx is the integral that gives us the area. And let's see. I feel like we've done the part I really care about, but let's fight this through to the end. The square root of x minus the negative square root of x is going to give us 2 the square root of x minus x squared dx. And remember that the square root is a power. We integrate it with the power root. So x to the 3/2, we divide by 3/2. That's the same as multiplying by 2/3. This constant 2 is sitting there. So we get 4/3 x to the 3/2 minus 1/3 x cubed, all evaluated from 0 to 1.5874. And now the least pleasant part of this problem isn't the calculus. It's just going to your calculator and typing in 4/3 times 1.5874 to the 3/2 power minus 1/3 times 1.5874 cubed. The only good news here is that when you plug 0 in, everything just turns to 0. So at least the thing you're subtracting is nice. And let me see if I can real quick find my notes and give you the decimal. It's about 1.3333. And that's it for us. There are all sorts of complications we could throw at you, but I don't wanna. If you want to see all the worst things that can happen, take the regular calculus sequence. I want you to go to leave this class understanding the basics of the areas between curves. And I hope we have gotten that from this section, these notes, and this video.